Okay, so today I'm going to talk about scalable automatic machine learning in H2O. And I promise all of those words actually are there for a reason. They're just not to get your attention or buzzwords. So how many of you have heard of H2O or used the package before? Okay, so for the record, that was everyone in the room, just for the video. Okay, good. So how many of you have heard of the AutoML functionality in H2O? Okay, cool. Okay, so that's what I'm going to talk about today. I'll talk a little bit at a high level what the H2O package is, but most of the talk is just going to be talking about this one function that we have in the package called AutoML. So first, just tell you what H2O is. So it's the name of the company that I work at, and it's also the name of the platform that we have. We also have a few other projects that I won't go into details about, but the main, I guess the project that has been the biggest and the longest at H2O is just called H2O. And at a high level, it's a machine learning platform that is meant, or let's not say meant, but the purpose in building it was to build a distributed machine learning platform that could work on big data sets. So if you can remember all the way back to 2012, I know it's a long time ago, but now everybody's talking about AI, but back then everybody was talking about big data. So that was the hotness at the time. So we made a machine learning platform that would work for big data. But these days, not a lot of, I won't say not a lot of people have big data, but a lot more people have smaller or medium-sized data than they do big data. So you can also just use it on your laptop as a regular R package. You don't need to run it on a cluster. Okay, so this is the overview of the talk. So I'm just going to say a little bit more about the H2O platform and then introduce just the concept of automatic machine learning. And then I'll talk about the H2O AutoML implementation, and then depending on time, I'll share some pro tips, but I might just skip over to showing some R Markdown files that we can look at some code. Okay, so I kind of talked about this already, but essentially H2O is a library that has many machine learning algorithms that you might be familiar with, like random forest, GBM, GLM, we have deep learning as well, and then some unsupervised algorithms as well. And everything, all the algorithms and the infrastructure is written in Java, which you guys, if you're here, you probably either don't like Java or don't care about Java. So you don't have to really know about that. You do have to install or have Java on your machine to run it, but that's about it. So for everybody here, the way that you would use it is the H2O R package. And you can get that from CRAN. You can also get it on our website. And some of the other features about it are we wanted to make a library where you didn't have to, so you could just deploy the models. So as a data scientist, you probably want to work in like R or Python, but then what used to be the case is people would prototype in R and Python, and then they'd have to hand over their models to another engineering team, and then they would have to recode everything from scratch so that they could put them into production. There's some other ways to do that now. There's a package called Plumber, which helps to deploy machine learning models. So one of the other features of H2O is that what you get from writing all this R code is you get basically a Java file that's a model that then can be deployed to production, and it's high performance and fast and something that engineers would like. So, and then this is sort of the most technical slide I have, but I'll just mention two concepts that we have in H2O. One is something that we call the H2O cluster. So this is just the name of the process in which all of the computing happens. So it's just a Java process running on your machine. And that's where all, as they say, the magic happens. So when you're writing our code that says, train a machine learning model, train a random forest, and it will communicate to the H2O cluster, which is just running on your machine, or it could be running on EC2 or some other remote place, and it will do all the training in there, and then you can get the results in R. And then just another concept is, so in R we have data frames, or we have data tables, or we have tibbles. So we have something called the H2O frame. It works exactly like a data frame, with the exception that behind the scenes, if you're running this on a cluster, some rows would be on one node, some rows would be on another node, etc. So that's how we do the distributed computing aspect. But when you're working with the H2O frame, it functions just like a data frame. And you don't have to learn a whole new set of operations for, manipulating the data frame. Okay, so that's the distributed computing part. You can kind of just skip over that if that's not interesting to you. Okay, so some of the other features. So I mentioned it's a machine learning platform. So what that means is we have, a bunch of algorithms that we've implemented, and then we also have a lot of supporting infrastructure around machine learning. So one of the things that is useful is when you're doing machine learning, you have to do some sort of pre-processing of your data sometimes, unless your data comes perfectly situated for machine learning. You might have to impute missing values. You might have to do some sort of normalization with certain algorithms. You might have to do different encodings if you have categorical data, like one-hot encoding is probably the most common. So we do all of that automatically. There are some other libraries that also do some of this stuff automatically, but a lot of them don't. So that's something that we have. Other things like cross-validation, grid search, random search. So we just have functions to do all of that. And then once you have the models, you can look at things like variable importance, model performance metrics, and you can do plots. So, so just to give you a reference point, other libraries that are similar to H2O in functionality are things like in Python would be scikit-learn. In R would be like caret or MLR, or maybe the tidy models. So just, you want a library where you don't have to leave and reach to all these other different libraries just to do your one machine learning task. Okay, so that's just at a high level what H2O library is. And you can look in our docs to see all the algorithms that we have. There's a lot of statistical learning stuff, so stuff that's not typical for a machine learning package. So probably a lot of you are statisticians. The advisors to H2O are Rob Tibshirani and Trevor Hasty, who are very well known, like machine learning statisticians. So, and that's kind of how I also identify, in the keynote this morning, we talked a lot about statisticians versus machine learning. There are some people in the middle, but yeah, there's typically a different viewpoint from the two sides. Okay, so automated machine learning. So this slide just kind of gives a high level, like what are some of the things that we do in machine learning in general, and then if we're automating the machine learning process, you'd have to automate all or some of these steps. So that would include like any sort of data preparation. Then once you have the data, situated, then typically you'd have to generate, some, small or large number of models. If your goal is to get the best model with the least amount of effort, then there's different techniques for doing that. And then this is sort of an optional part, but ensembles is, at least in my perspective, something that's important if your goal is to get the best performing model. And that might be not the goal. Maybe your goal is to have the most interpretable model, then you might take a different approach. But yeah, so let's move on. So this is just a little bit more about what each of these things mean. So with data preprocessing, that would include things that I've already mentioned, imputation, one-hot encoding. That could also include feature selection, feature extraction, and then all sorts of different types of encodings of categorical features. This last point is important. So this is something that you maybe haven't heard about, but if you If you're familiar with the data science platform Kaggle, where people are competing to get the best score, that's where you'll see people using some of these methods. I know that there's not a lot of literature on this topic, although Max Kuhn, the creator of Carrot, he is now writing a book called Feature Engineering, and he has some information on this, and it's an online book, so you can look that up if you want to learn more about different types of encoding of categorical features. So in model generation, typically what you do if you want to get a bunch of models, you could do a grid search or a random search. That's the most straightforward way. There's other techniques like Bayesian hyperparameter optimization. There's some newer techniques, one called hyperband. Then there's a combination of those two called, I forget the acronym, it's either BHOB or BOHB, BOHB, Bayesian optimization with hyperband. So there's all these different techniques for tuning your models, essentially, or doing model selection. And then in terms of ensembles, there's a few ways. Once you have a big collection of models, you could either choose the best one out of that set, or you could try to ensemble all of them together or some subset of the models together to get a better model. And there's different techniques. The one that I typically use is called stacking or superlearning. Another popular one is called ensemble selection. And so the term AutoML it's a very generic term and it's not well defined. So so H2O AutoML, which has been in the H2O package for I think almost 2 years now. That came out a little while ago. Then Google released a tool called Google Cloud AutoML, and so then that started to confuse people, like what is AutoML and did Google invent AutoML? And so people were asking us these questions quite a bit. So I wrote a blog post that explains all the different types of AutoML and what they're used for. And essentially, you can break it down into use case. So like if you have image data, you're going to want to use deep learning, and AutoML in the deep learning sense is something that they call neural architecture search. So that's a very specific type of thing, and that's actually what the Google AutoML tool does. If you have more standard data, like tabular data that's either numeric or categorical, then you would use a different set of tools probably, because as Norm mentioned earlier, deep learning doesn't actually, that's not the forte of deep learning. Deep learning is very useful for images and can be text or time series data. But for the traditional data sets that we see more often in business, that's not the forte. So if you're interested, you can read this blog post, or if you want to find references to other tools, there's some in there as well. Okay, so here's that previous slide that I had, but I'm highlighting some of the stuff that we have in the H2O AutoML. So before I'm sort of speaking generally about what is AutoML, and now I want to narrow in a little bit and say what do we have in the H2O AutoML version. So in terms of data preprocessing, it's pretty straightforward. We have just all the same stuff that we have in all the H2O algorithms, and those two other bullet points are things that will go into H2O. We almost got target encoding into this latest release, but it didn't get in time, so that will go into the next one. And that's, as I mentioned, it's important if you have like high cardinality categorical columns, like for example, a zip code or something like that. So if you have a data set and one of your columns is zip code and you try to give that to a machine learning algorithm, it's just going to be chaos. It's either going to think it's numeric and do something weird there, or if it knows it's categorical, it's going to maybe try to expand that into like 40 or 50,000 columns, and then bad things will happen. So you need to do some sort of encoding when you have these high cardinality categorical columns in your data. And if you want to build an AutoML tool, it has to be prepared for stuff like that. Otherwise, people use it, it blows up, and nobody knows what's going on. Okay, and so then in terms of model generation, what we do right now at least is we do random grid search over all the algorithms that we have in H2O, and then we tune them you know, it says validation set, but we actually changed that to do cross-validation. So, so now the individual models are tuned using cross-validation. And then what we do once we have all these models is that we create stacked ensembles from them. And so why do we choose this strategy? So, well, so first of all, in H2O, we're always looking for strategies that scale well, that can be done fast and on big data. So, or in parallel. So grid search and random search are good with that. Some of the other methods like Bayesian optimization are sequential. So you're forced to train one model and then you get some results and then you train another model. Like that, so it's it can be it's not suited for parallelization, I guess you could say. However, we are also working on adding that. So you'll probably see all of these methods at some point in H2O. So we basically just built the first version with whatever we already had in H2O, and then we're adding new methods as we go along. So again, why random grid search and stacking? So the reason is that these two things work actually pretty well together. And the reason for that is because, so stacked ensembles perform well when you have a diverse set of models in the set. So, so one way to get diversity is just to use randomness. So you can just create a random set of models and then they're sort of guaranteed to be diverse. And so that's why those two things work well together. And I'll explain a little bit. Let's see how we are doing on time. I'll just for a minute explain what stacking is in case you know, you came here to learn something new. So how many of you have heard of stacked ensembles or know how they work? Okay, so like a few people. All right, so I'm going to, it's very simple and you could write this in, you know, our code pretty easily. And so let me just explain how it works. So you have your training set, let's say it's n rows, m columns, and your response column y. So that's your, you know, your training data. And the first thing you do if you're going to want to do stacking is you perform k-fold cross-validation. There are variants of stacking that you don't need that, and we actually have that as well in H2O, but I'm going to talk about the traditional form, which is do k-fold cross-validation with a bunch of algorithms on your data. So maybe do a random forest, a GBM, a deep neural net, and a GLM or something like that. And then once you do cross-validation, one of the artifacts that you get from that is you get a column of cross-validated predicted values. And so that looks like that. So each algorithm, let's say you have L, so in this case we named 4 algorithms. So we get 4 columns of cross-validated predicted values. And then we combine those into a new matrix. And so the dimension of that is still going to be n, number of training samples, and then in this case it would be 4 columns. And that's what they call the level 1 data. And this is, you train a machine learning algorithm, and it could be any algorithm, on this data. So there's like 2 sets of machine learning layers happening here, and this is called the meta learning step. And so what this algorithm does is it learns how to take the output from the algorithms and predict the original response. So that's its job, and so that's what you're training it to do. And typically we use GLM for this. It's pretty robust, but you could use all different types of supervised learning. And so that's essentially what you're doing. So you're just using machine learning to learn what the best combination of those base learners is. So that was a little fast, but yeah, so we'll just leave it there. So, okay, so just a little bit more of an overview. So H2O AutoML, we do the basic preprocessing. We train, I guess I should speak into the microphone, train a random grid of GBMs, deep neural networks, GLMs, etc. So this part is actually the hard part. And by hard, I mean, when you're a data scientist, one of the most difficult decisions that you have to make is how to spend your time training models. So which algorithms do you choose, and then once you, let's say you choose a GBM, then you have to decide which hyperparameters do you want to tune, and then what ranges do you want to use. So unless you're pretty comfortable and familiar with each algorithm, that's kind of the hard part. So we, I think, have, I mean, this is sort of the art of AutoML, but we've selected what we think are important hyperparameters and ranges and just put them in there and defined what the random grid is for each of these spaces. And that will be continuously tweaked as we get more benchmarks of our tool, and maybe we, that will evolve over time. But we kind of just took a first pass and said, what kind of makes sense based on, talking with all the, data scientists at H2O, a lot of whom are Kaggle grandmasters, so they're very good at this. And we came up with what we think is a reasonable grid for each of these algorithms. And then once we have all the, okay, so I'll also say, how does this work? Well, the interface of the AutoML function, it basically requires you to say how long do you want this to run for. So you could say, I want you to run this for 3 hours, or I want you to run it for 20 models. So you can either specify it by models or by time. And that's basically your only job. You say, what is your data set? What are you trying to predict? And how long do you want it to work for? And so at the end of that time period, it will train 2 stacked ensembles, one with all of the models, which is typically going to give you the best performance. But if you ran it for, let's say, 1,000 models, you might not want to, let's say, put that model into production. It might be a little too complicated. So then we have another more lightweight ensemble, which just takes the best of each of the algorithms. So it will take the best GBM, best DNN, etc., and make like a little baby ensemble. And then what you get back from the AutoML function is what we call the leaderboard. And that's just a ranking of all the models based on cross-validated performance. So this is actually what the interface looks like. So you just load up the H2O library. And something that you wouldn't be familiar with if you haven't used H2O is just this one function that you have to do at the very beginning of any H2O script, which is H2O.init, and that will start up the H2O cluster on your machine. Or it could connect to one that's already running. And there's various parameters that you can specify with that function. Like you can control the amount of memory that you give it. You can point it to a remote IP address or remote port, etc. But for the most part, you're running this on your laptop. It's your first time, just do H2O.init. And then you need some training data. So H2O.import file is essentially read CSV. But instead of reading the data into our memory, it totally bypasses that. It goes right into Java, into the H2O cluster. And so there's no copying of data from R to Java. It just goes right from disk and in a very fast way, reads it in. So now we have some training data. Let's say that's a data frame called train. And now we can run AutoML. So, and you might be asking, oh, where's the test set or the validation set? So that will be done all automatically unless you want to specify, a validation frame or what we call the leaderboard frame, which would be a test set to score the leaderboard on. So if you just give it a training set, it's going to score by cross-validated performance. So in this case, we just say why. So in all the H2O algorithms, we have a little bit different interface than maybe you're used to if you're doing other machine learning in R. So in R, typically we have an X and a Y. You can also use the formula interface in a lot of cases with R. But in H2O, we have training frame is just your H2O frame, and then we have Y would be the response column name or the index. And then if you want to specify some subset of the columns as your predictors, you can specify that with X. So that would just be a character vector of names or indices. So that's just a little bit weird if you're used to regular R modeling packages. Okay, so if you don't specify X, it will just assume everything that's not the response column is your predictors. And then this, we're saying run for 10 minutes, so 600 seconds. and then it will go and run, and then what you get back is an AutoML object. And one of the things in that object is the leaderboard. And then I'll show you the leaderboard in a minute, but I just wanted to also briefly show you our GUI. So H2O, when you're running it, if you go, so H2O starts on a particular port. So if you, in the default is localhost port 54321. So if you type that into your browser, this thing that we call H2O Flow will pop up. And so you can see all your models in there. You can interact with them. And you could even train models in Flow and inspect them in R or vice versa. We basically built this thing to show people H2O, because when you're trying to be a company, getting people excited about buying enterprise support for open source software, and you show them like R code, they don't get very excited. So we built this as sort of a more pretty version, but now a lot of people just use this instead of any of our programmatic interfaces. You can do everything. You can't really do data munging in here, but you can train all the models and do whatever just by clicking. Anyway, this is what the AutoML interface looks like in Flow. Okay, so this is what a leaderboard looks like. So this would be for binary classification. So for all the different tasks, let's say binary classification, multi-class, and regression, those are the 3 tasks that we do. You get a different looking leaderboard because each of those tasks have a different set of metrics that are appropriate. So, so binary classification, we have a certain subset of metrics that we think are useful, and we rank by AUC by default in binary classification, but that's another parameter that you can set in the AutoML interface. You could say, I want you to score by log loss or by MSE, and then it will rank based on those metrics, and choose the leader based on whichever has the highest or lowest of one of those metrics. So it might be a little bit hard to read, especially from the back, but so I'll just kind of tell you a little bit what you see here. So the first 2 models are stacked ensembles. So the first one is the all models stacked ensemble, which is typically what we see. It's not always, but for the most part, that's going to be your best model. And I'll also mention, if you don't want to use any of the algorithms, you can turn on and off ones that you like or don't like. I would say if you're running it for the first time on a data set, just run them all, but maybe after some experimentation, you realize that you don't want it to spend any time on deep learning, so you shut that off. So you can also shut off the stacked ensembles if that's not something you're interested in. And then what we see next is, let's see, like 5 different XGBoost models. So XGBoost is another very popular machine learning package. It just does boosting. Well, I think you can also do random forest through XGBoost, but essentially it's a gradient boosting algorithm. It's very popular on Kaggle, and H2O has its own GBM implementation, but because XGBoost is so popular, we put it also into H2O. So you can use XGBoost from there. So, and it does pretty well most of the time. And so we see that happening on our leaderboard. Then the next few models are H2O GBMs, and then another XGBoost. And then as you go further down on this particular problem, then we get a few random forests, we get some deep learning. And at the very bottom, we get a GLM. So you can see all the AUCs, and what you're actually seeing is the model ID. So for each one of these models, if you're more interested to know, okay, for that first XGBoost model, what were the parameters used? You just ask H2O, you say H2O.getModel, and then put the model ID in there, and you grab the model into memory, and then you can look at all the parameters and do whatever you want with the model. Okay, let me check my time. Okay, so also, since probably most of you are new to using this tool, I'll just give you a few tips. It's very straightforward, but there's a few things that can make your experience a little bit better. So this is you about to have an expensive AWS bill, so be careful. So actually, one of the defaults that we have is that The default is that it will run for 1 hour, so you don't really screw yourself. But that also is one of the things that I'd like to mention is you run it, let's say you think it's going to run for like a long time, but the default is it's going to cut itself off after an hour. So if you want it to run for more than an hour, you have to use the max runtime seconds argument and set it to something longer. So I mentioned this already. This is the exclude algos parameter. So if you have like very sort of weird data that you know is not going to do well with certain algorithms, you can turn on and off the different algorithms. We also just added include algos because people wanted to include them rather than exclude them. I don't know why, but you know, it was a good suggestion, I guess. So, and why might you want to do this? So, for example, if you are doing some sort of text classification problem, and let's say your data is very wide and sparse, maybe you don't want to use tree methods, for example. Like maybe you could just let it use, you know, deep learning or GLMs and see what happens. I, again, would still recommend just trying it and see what happens. And then if things seem to, you know, be taking too long, or it's not training enough models, or it's, you know, spending too much time on the tree-based models, then you could turn it off. But one thing I want to say about this is sometimes it could be tempting to just take out all the algorithms that are not performing well. So, for example, GLM's hardly ever going to beat a GBM, but for the ensemble, it's actually mostly useful to have those models in there, even if they're not very good objectively. So, because the added diversity can help in the ensemble sometimes. And so if it's completely useless in then the ensemble should learn that and ignore it. So it's kind of like safe to just keep it in for the first time. And if you notice, you know, that let's say you use a GLM meta-learner, which is the default, and you see the coefficients are 0 for all these different algorithms, then you might, you know, later decide to just turn them off because they're not being used. So things like that are stuff to think about. I mentioned this already. So the default is that it will run for 1 hour. Another question that we get is we have a seed argument, but it doesn't guarantee reproducibility. It's a trick. So it does guarantee mostly reproducibility, but there's some things that can affect that. So what the seed will do is it will control, of course, like cross-validation splits. It will control the hyperparameter random search grid. So if you run it twice with the same seed, you'll be guaranteed to get the same random hyperparameters that it's going to try. But there's a few things. For example, if you're running AutoML by time, then if you ran it once and you had, you know, some other processes running on your machine, and then the second time you had no other processes running on your machine, it might get more done the second time in that same amount of time. So maybe it has more resources, so it can train a few more models, and then your results will be slightly different. The stacked ensemble will be slightly different. The leaderboard might be slightly different. And the other thing is that the deep learning implementation in H2O is not reproducible unless you run it on one core, and that would be very slow. So that's just a design decision. It leads to like a very fast implementation, but it's not reproducible. So again, then all the other models might be the same, but then the deep learning one would be slightly different, and then possibly the stacked ensemble would be slightly different. So, so just to note, if you want reproducibility, like full reproducibility, you have to use the max models argument, because that will guarantee you train the same number of models each time. You have to use the seed, and you would have to turn off deep learning. Okay, so another tip is, so something to think about, which you're not probably used to thinking about if you're an R user. I know I wasn't when I first started working with H2O, is memory. So when we start the H2O cluster, we're giving that Java process a certain amount of memory to do what it needs to do. And all of the models, all of the data, everything's happening in that Java process. And so if you're running AutoML for a very long time, let's say you train 1,000 models, you need to have enough memory to store 1,000 models. So the default, when you start H2O in R, is 4 gigs. And that's just to safely run on most machines and without any problems. However, like if you're doing a big experiment, you probably want to increase that to something bigger, like something just, if you have a machine dedicated to this task, let's say you have a 100 gig machine, then maybe you give it 95 gigs and let it do its thing. If you're running it on your laptop and you have other stuff going on, you're browsing Twitter, you're on Slack, etc., you have to maybe give it not all your memory. Okay, so basically this is just something to think about. If you start to see problems, maybe remember this and say, oh, maybe I should give it more memory. But if you're working with like small or medium data, it shouldn't be a problem. Okay, so this is like afterwards. Now you've done your, so this is the future of data science right here. Lots of naps. All right, so once you're done with training AutoML, so what are some things to look out for? Let's see. I'm going to skip this because I want to show you the code. I'll mention one thing. So if you want to, one way to do this is to train a few models, stop and look at the results and see how things are going, because maybe you don't know in advance, like how long is it going to take. So maybe just start with 10 models or 20 models, and then observe what you have there. And then what you can do is you can add models to that existing project. You don't have to start over from scratch. And to do that, just look up the project name parameter in the docs and you'll see how that's used. So you just have to specify the same project name every time and it will add models. And if you change the seed, it will add different models. So that's also something to know about. Okay, I'm going to skip that. I'll mention just a few things from the roadmap. I already mentioned that we're working on better support for wide data sets. We will support text directly because we have a Word2Vec implementation in H2O, and we're going to essentially just put that in the front and then process it, turn it into numeric data, and then apply AutoML. Okay, so I want to just point you to some code so that you can try it out. So we have examples. So I'll leave that up there for a few seconds, but I guess also these slides are going to be online, so I don't need to do that. So the documentation page is a good place to start, just to get a sense of what's going on here. Let me make this a little bigger. So if you go to docs.h2o.ai, you'll eventually find this. And it just explains better all the parameters and gives you some examples and has a few more, lists all the algorithms and what we do, etc. And, oopsies. Oh, no, okay. And then the tutorials that I wanted to show you is here. So we'll just look at, let's say, the binary classification example, and I'm just going to click on the HTML version so that you can see all the output. So this will look very similar to the code that I showed you, where the task here is, let's see, let's go down to the data. It's this product back orders data set. So you're just supposed to predict whether or not a product is on back order. And we load the data, we run it for 10 models, and then we look at the leaderboard and we can see, here's the stacked ensemble doing the best, and XGBoost models, etc. Just shows you how to look at the whole leaderboard because by default it'll only print out the head. Then it gives you some more things that you can do with ensembles. You can look inside of the ensembles to see how each of the algorithms is contributing to the ensemble, which is kind of interesting. And then it shows you how to save the models. But I think I only have a few minutes left, so I just wanted to save that for any questions, and then just say if you want to contribute to H2O, you don't have to know Java. You can contribute via R. There's my contact information, but I'll just leave a few minutes for questions.
When it comes to deep learning, how much is it customizable? Can I choose the architecture? Can I choose different hyperparameter selection than the standard ones?
Yeah, so the question is about how customizable is the deep learning, but I'll answer that more generally because so in the AutoML interface right now, the thing that you can control is which algorithms turn on or off, and that's about it. So in the future, we'll allow you to actually customize the grids or add specific models or grids that you want to do. The deep learning function in H2O is fully customizable. So if you wanted to, you can specify, number of layers, number of nodes per layer, dropout rate, like there's like 60, too many parameters basically. So we've just gone and defined what we think are, reasonable things.
I have a related question there. How do you do your releases? You said you pick good tuning parameters. You pick them as new things comes in. So if I run one, what happens next month? So how do you deal with it?
Well, yeah. So unlike all of our other algorithms, which are expected to be sort of fixed over time between releases, unless there's a bug that we're fixing, the AutoML algorithm can change over time, essentially. So we're doing a lot of benchmarking to make sure that we're not just overfitting it to some small set of data sets that I like to play around with. But so essentially, we benchmark them on a large number of data. Like if I have an idea, like let's try out like changing this thing or adding, this grid in a different way, I would want to be pretty confident that that would generally be a better result. So that's kind of how we're the iteration process. And something else that I'm working on right now with other collaborators. So if you've heard of openml.org, they are a platform, a nonprofit, but also a platform for machine learning benchmarking. And we're working on like a very comprehensive open source AutoML benchmark of all the AutoML tools. And through that, that's sort of, that's what right now what I'm using for benchmarking. I think I answered your question. I'm not sure. Okay.
We can take one more question.
So I have a question about the other performance. You were talking before of these big models and then the little one which takes just the best ones. And you were saying maybe you want to use the other one in production, and I thought maybe because it's less computationally expensive also to use the other one. Is that the reason? And how do they decide it? Does this have some number that will tell me approximately how expensive is one with respect to the other?
No, I mean, the one with fewer models in it will be faster to do predictions. So it depends on what your use case is, and H2O is designed for, production models where you have sort of like sub-millisecond prediction speeds. So if that's not the type of thing that you think about, then either one is fine. But if you're deploying a model in production and you need like the absolute fastest thing ever, well, you could use a GLM, but then you could also, use a small tree or something like that. So I would say it's just something that you would have to measure. You could try both, and you could try the best one and see if it's fast enough for predictions, because that's really what we're talking about is prediction speed. And the way that it works is it has to make predictions from all the base models and then feed that into the meta learner and then make another prediction. So if you have, and essentially it's not in parallel unless you were to write some custom code on your server